Great. Thank you very much, Wei Han, and thank you all of you for making it to the end. So my talk is about multi-scale modeling of battery degradation. There's a couple of equations here, but hopefully I won't make it too heavy given the time of day that we're at. So first of all, diving straight into the problem, you might be asking, how do we make better batteries? And as the name of the talk suggests, we need to consider multiple length scales of interest. First of all, we've got chemistry. Do we have the right materials that give us the lifetime, the right energy density? And we've heard a whole range of talks during this very interesting conference series about how we can dope material, use high nickel, LFP, and so on. But beyond that, we also need to consider, with that type of material, what is the microstructure of that material? We've heard things from people like Jeff Dahn about polycrystalline materials and single crystals, and also the size of the particles influences the capability of that battery, whether it's an energy cell versus a power cell. From there, we also need to consider what form factor or shape of battery do we have, because cylindrical batteries, whilst they might be easy to manufacture at scale, there are certain challenges around the how heterogeneous the pressure distribution is in that system. And then finally, a electric vehicle is not just made up of a single battery, it's made up of thousands of batteries connected in series and parallel, and there are different dynamics that kind of propagate from the materials levels to the system level. So really, this is a multi-length scale problem, so we need to leverage insights from all of these different length scales to answer that question of how to make better batteries. Now, within this realm of multi-scale battery degradation, we need to think about what actually goes on in a battery. Now, if we only focus on the electrodes, because there are degradation modes in the current collectors, separators, and the electrolytes, you can see some of the prominent degradation modes that people consider. So on the anode, probably the most famous one is the growth of the solid electrolyte interface layer, or SEI, which contributes to loss of lithium inventory, which is basically how much lithium do you have in your system and how much of that do you lose as you age your battery, because graphite is thermodynamically unstable in most organic electrolytes. As you charge as you charge and discharge your battery, the material will expand and contract, and that will cause mechanical pulverization of your system as well. And then there are other different degradation modes, like if you fast charge, you've heard lots about lithium plating, and also at the cathode. People don't talk enough about the cathode, but actually there's loads of really important degradation modes, like phase transitions, transition metal, migration, and so on, that we need to capture as well. So I'm not going to go into all of them, but I'm going to focus on the chemomechanics of the problem and look at how we can understand how particle cracking influences degradation. So my talk is ultimately about modeling, but we'll also be leveraging off some testing as well. So you might ask yourself, how do we model a battery? And if we think about the key components in a battery, we've got an anode, which is a composite. It's made up of a polymeric binder, a carbon additive, which improves the electrical conductivity, and then your active material. And you've got the similar sort of system on the cathode as well, but we have a transition metal oxide. And then in between, we have a microporous separator and then a liquid electrolyte between them. If we zoom into those different regions, we can see that we've got different interfaces, like the solid electrolyte interface between the active material, but also the binder. So when we model these batteries, what we're trying to do is solve the physical equations associated with diffusion in the liquid phase as lithium ions move around, diffusion in the solid phase as lithium moves through the solid electrodes, and then the potential in each one of those phases. Now, in this talk, what I'm going to focus on is chemomechanics, which is basically how electrochemistry and the mechanical properties of the material interact with each other. And this was some really nice work from Jake Christensen's group a while ago, where they cycled a battery at very high C rates, and then they took apart the cell, did a cross-section of it. And what you can find is that near the electrode separator interface, you get a large degree of mechanical pulverization of those particles. Graphite, as you charge and discharge it, expands and contracts by about 10 volume%. It's a little bit less in the cathode, but the problem with the cathode is that the Young's modulus is very high, so it's a very stiff material. It behaves like a ceramic-like material. And that can lead to cracking of the material, which accelerates SCI layer growth as you have more surface area and a whole range of other properties as well. So we want to understand this. Obviously, this is an image at the electrode level, but we'll start off by looking at how to solve this problem from the particle level. That's our lowest level of consideration here. So there's a few equations, but there won't be too much. But one of the tools that we use is called phase field fatigue modeling. So for people not familiar with phase field modeling, a phase is a region of a material with uniform physical and chemical properties. So you'll have come across phases like water is liquid at room temperature, but it becomes ice at lower temperatures and steam at higher temperatures. And we have solid phases as well. So what we do is that we use our phase field fatigue crack model to describe how lithium moves in and out of materials. And what we can do is we can describe damaged regions. So where do we have a crack and where do we have normal regions of material? What we also do is we introduce fatigue into the model. So probably you've seen fatigue in a range of different applications. So metals, for example, if you take a paper clip and you bend it back and forth, you will fatigue the material as it work hardens and you decrease the crystal size in your material. And a similar sort of effect happens in lithium-ion batteries, that as you stress your material over time, you will change the fracture toughness properties of that material. So phase field modeling allows us to understand how materials crack over time. So with this modeling framework, we start from an idealized spherical particle. So we assume our cathode, in this case, is a perfect sphere. We've introduced a defect into that material. And in our simulations, we can describe the concentration gradient in that material, but also the stresses in and near a crack. And what you often find is that near a cracked region, you often get different concentration profiles, which lead to a heterogeneous stress in the material. And this is what the stress profile and concentration profile might look like at the beginning, so about 50 cycles in. But as we cycle our battery, what will happen is that the stress near a crack is generally higher. That leads to that crack opening out wider and wider. That leads to more surface area, so more cathode electrolyte interfaces being revealed, and growth of what we call the CEI, or cathode electrolyte interface. And this is normally focused around cracks. And this is important because essentially, if you're manufacturing your battery, you want to remove as many of those defects as possible. If you calendar your electrode as well, you will often introduce cracks into the system. So over calendaring your battery electrode can actually lead to poor lifetime because you introduce these cracked properties. Now, if we retain our idealized spherical particles for a moment, you might say, okay, that's all good and well. I know cracks exist. But how is that useful for me in terms of designing my material? Well, what we can do is we can take these phase field models and then we can change different parameters. So first of all, if we assume that we have a 5 micron cathode particle and we have a crack size which is approximately 2% of the radius of the material, we can obviously run through different C rates of that particle. And what we can find is that there is a critical C rate below which we don't really get any cracking at all. So in this case, using the properties that we've looked at, below 2C, you are unlikely to get any appreciable crack growth in the system. You'll also note that you get two different regimes of operation where you have unsteady crack growth, where just like a ceramic will crack very abruptly. That is what we call unsteady crack growth. And then you also have more stable crack growth, which you might get in more plastic materials, where if you've got a polymer, you can see that crack growing very slowly. And what causes this nonlinear behavior is this kind of degradation in the fatigue strength of the material. And we can describe that with our phase field models. Similarly, we can change our particle radius if you've got that ability in your battery manufacturing. And again, in this case, what we do is we fix the C rate to say, I want a C rate of 2. What is the particle radius that I should have my system designed to avoid any appreciable cracking? And in this case, what we find is that if you have 2C as your design C rate operation point, then broadly speaking, below 6 microns, you're not going to get any appreciable particle damage. And that's really useful for cell manufacturers. Now, obviously in this example, I've used an idealized spherical particle, but in reality, we don't have perfect spheres. So what we can do is we can do X-ray tomography of battery materials and reconstruct the real morphology. We introduce a half-penny crack, so again, hypothetical, but then we have a look at how the real morphology might evolve over time. And this is what we see, that we get this very dynamic behavior. Initially, we have a very slow crack growth rate in the material, but then all of a sudden we get a very fast acceleration in that crack growth, and that leads to a separation of the two materials. Because what you find in these real morphologies is that you can get cracks that agglomerate, they merge together, and that changes the dynamics of the crack growth in the system. So in real systems, obviously, it's a lot more complex, but the theoretical perspective gives us an upper bound of what we can actually achieve. So that's just to kind of temper that every model you see is slightly wrong. It's just how wrong they actually are. But they do provide us with a good guidance of where we can go and so on. Now, again, another caveat is that in our system, we've assumed we've got a single crystal. And what we know is that in reality, we have these kind of primary and secondary particles. And if you have a look at this FIB-SEM tomography, where we slice through an electrode, you can see that you often get cracks that grow preferentially along grain boundaries. And that's something that we haven't quite captured yet. It's not something we've done yet, but it is future work that we will move along. But again, something to caveat us with. Now, this is a talk about multi-scale modeling. And what we're going to do now is go up one length scale and look at the whole electrode length scale. The video you see here is an X-ray reconstruction of a coin cell. It's a relatively thick electrode, so if you can see from the diagram, it's 400 microns. And again, we do multi-scale imaging. We can capture the entire coin cell. We can digitally strip away the steel casing to reveal the active material. So the red phase is the active material, and the blue phase is the pore. And then we can do higher resolution imaging. And what we did here, so this was some data from my colleague Paul Shearing at UCL in London, is that you can take an XCT image of your battery before charging and then after charging. And then you can use a technique called digital image correlation or digital volume correlation and compare the size of the particles before and after. And what you see is the result on the right-hand side, which shows you that where you get changes in lithiation. And normally what you find in conventional lithium-ion batteries is that particles near the electrode separator interface lithiate more because that's the path of least resistance. But in this case, what we find is that we get large amounts of expansion and contraction near the electrode current collector interface. Because what you'll notice is that in this electrode, it's extremely thick. It's actually a manganese-based electrode, which generally has poor electronic conductivity. And this is actually quite detrimental because if you lose electronic percolation in your system, so you get no electron transport to the rest of the system, you've effectively lost that active material. So it's important to understand whether your system is ionically limited or if it's electronically limited. And I think people generally assume that we're never going to be electronically limited, but that's not actually true here. So now that we're at the electrode continuum level, what can we do? We've got this range of models. So this is where we start to introduce continuum level models, where there's a range of different types. You've got single particle models, the Doyle-Fuller-Newman type models, and homogeneous models. And we've developed this software called PyBAM, which is a Python-based open source modeling tool, which allows people to use this. You can use it yourself. And what PyBAM does is that it solves a series of those equations I described earlier. So we describe diffusion in the solid phase. So we use a spherical Fickian diffusion equation, and we also solve for the potential difference in the solid phase. And also we solve for diffusion in the electrolyte and also the potential in the electrolyte. And we couple that together with a Butler-Volmer equation to describe where the reactions are happening. And why is that useful? Is that it allows us to describe where the electrochemical reactions are happening. It's not homogeneous across the electrode. It's normally higher near the electrode separator interface, and also how concentration gradients build up, which will ultimately influence the behavior of your battery. But as I mentioned, we're going to keep this stream of consciousness around chemomechanics, and we're going to describe electrode stresses and how they evolve over time. So here we've got a diagram of the anode and cathode and also the stresses involved. And when we start discharging the battery, as I mentioned, we generally get high stresses near the electrode separator interface. And because the cathode is normally ceramic-like, ceramics are very good under compression, but they're terrible under tension, right? So what you find is that when we initially discharge our battery, the particles near that electrode separator interface at the surface undergo a very high tensile stress. At the center, it undergoes a very compressive stress because it always has to balance. But over time, as we discharge our battery, that peak stress propagates backwards to the electrode current collector interface, which can be quite detrimental. Then when we switch our operating mode to charge, again, we get the peak current density at the electrode separator interface, but this time we get a switch between the compressive and the tensile forces involved. And again, you get that propagation of the stress wave through the system. So to kind of summarize the behavior, if you looked at the peak stresses and look back at the original Christensen work where they took that experimental cross-section, what we can do with our continuum level models is look at the peak stress at different locations on the different C rates. And again, you get a good description of that peak stress. And obviously, if you want to avoid this particle fragmentation, you can use these guidelines to kind of say, I don't want to operate above 2C or so on to minimize the stresses. Now, in our continuum model, we can then take that stress and then integrate it with a crack model. We typically use something called Paris law to describe how a crack grows over time, and then relate that new surface area that we've generated to the growth of the SCI layer, and then ultimately describe how the battery degrades over time. And we've got all of this integrated into PyBound. Now, if we take one more step forward, a lot of people now are looking at silicon, and silicon's great. If you look at the gravimetric specific capacity, it's got 10 times the specific capacity compared to graphite. But as you know, the volume expansion leads to cracking in the material. So we want to understand what actually happens when you make these graphite silicon composite systems. So again, what we can do is we can describe the behavior of silicon and behavior of graphite in our continuum level models. If you look on the bottom left-hand side curve, you can see the open circuit voltage curves of both graphite and silicon. Silicon has some interesting features that it has a huge hysteresis, because as you charge and discharge silicon, it's not an intercalation mechanism, it's an alloying mechanism. And you go through different phase transitions. You go from an amorphous phase to a crystalline phase, and it's path dependent. So when you reverse your intercalation or deintercalation, or lithiation or delithiation, what you find is that you have different open circuit voltages. And that can be a problem for state estimation, like state of charge estimation, but it has a huge implication in terms of which phase is electrochemically active. And what you find is that essentially, when you have a graphite silicon composite anode, essentially the graphite does the majority of the work at the high states of charge. So silicon is almost inactive between 100% and about 30% state of charge. It's all the graphite. But then when you use that lower state of charge range, the silicon suddenly becomes very active. And if you calculated what the reaction current density is, it's actually very detrimental. So this is important because if you select your state of charge range, it can drastically influence the lifetime of your system. So here what you can see is some test data from an LGM50 cell, which has a graphite silicon anode. And if you cycle it over 100 to 0% state of charge, you get pretty decent lifetime. And again, we can separate out the loss of lithium active material in the graphite and the silicon. But if you only cycled in that 30% regime, where silicon is extremely active, what you find is that essentially you start to pulverize your silicon. So this is really useful for, again, extending the lifetime through intelligent control of your system. Now, the final length scale of interest is what happens when we integrate cells into battery packs. So obviously, a battery electric vehicle is not just a single cell, it's multiple thousands of cells connected in series in parallel. And if we think about this problem, we basically assume that in our parallel configuration, all cells give the same current. So you might be discharging at an effective C rate of 2C, but in reality, not all cells behave the same. Some cells actually give much more current than other cells, and that can be very detrimental. You might be thinking you're operating at 2C, but one cell is actually acting at 4C. So what causes that difference is actually due to the balancing of the resistance network in the system. So here you can see we've got 6 cells in parallel, and there's finite interconnection resistances between each one. And what that can do is that can drive heterogeneous currents in the system. And if we assume we have all the same cells, so it's only the influence of the interconnection resistance, you can see that one cell basically delivers twice as much current as another cell. Generally, it's near the load point, so the path of least resistance, where there's most current. Now, if you have a bad cell, so a cell with a higher impedance, if you place that at location 6, you actually exacerbate this kind of heterogeneous current effect. So you really don't want to put it in that position. If you actually placed it at location 1, which normally gives you more current, you can actually homogenize some of those uneven currents, and that can lead to an improvement in performance. So if you were to generate a Ragone plot of this system, what you find is that actually intelligent placing of cells can give you about 10% extra accessible energy, which actually is quite significant just from where you place the cell in your system. So that's one thing to consider. How do currents distribute through the system? But obviously, this talks about degradation. So when we look at the degradation in our system, there are some degradation modes which depend on the amount of current going through them. So we looked at particle cracking earlier. And generally speaking, in battery packs, there are 2 main modes of degradation. There are convergent degradation mechanisms where initially one cell gives more current, and then maybe it degrades more, and therefore its resistance increases, and actually it pushes the load onto the other cells. That's actually the ideal scenario, that you spread the load across everything. But you can also get divergent degradation modes where actually you get like a positive feedback effect where the worst cell keeps getting worse, and that's not what you want, right? So what we did is we did a large amount of degradation studies to kind of look at that. So we have 3 different battery packs. So the simplest battery pack is just 2 cells in parallel. We can control the temperature of each one independently because we developed a rig to do that. And the first thing you can see is that, one, at higher temperatures, you get more accessible energy. That makes sense. But the interesting thing is that for the lower temperature cell, the degradation rate is actually faster than the one at the higher temperature. Normally, convention tells us that higher temperatures give us higher SEI layer growth, and that should be the dominant mechanism. But that's not what we see here. Beyond that, what we also see is that there's a difference in the degradation between 2 cells in parallel. And depending on the thermal gradient that we have across the system, the first cell, a B1 or B2, could be the dominant one. And I'll unpack that a little bit in a moment. So in our system, we've designed a battery pack where we can periodically remove cells from the system and diagnose them. So what we can do is we can measure the resistance of each one. So this is the resistance of the cells as we cycled them for the room temperature, for the high temperature cell, first of all. What you see is that, okay, there's an average increase in the resistance, as you'd expect from SEI layer growth and so on. But the 2 cells are more or less even. They're degrading at more or less the same rate. However, as we start to decrease the temperature, what you find is that at the end of life, the divergence between the cell parameters starts to increase. So that's at 35 degrees, 32 degrees. And then if we go down to room temperature, we get a huge difference between the impedance of the 2 cells. And we might think, why is that, right? So post-discharge and also EIS studies allows us to understand the impedance, but there's also the thermodynamic losses in the system. So what we can do is we can discharge the battery, get the voltage curves, and then we can apply what we call degradation analysis, where there's 3 main modes of degradation in a battery: loss of active material in the anode, loss of active material in the cathode, and loss of lithium inventory. And what you see here is that as we increase the temperature of our battery, broadly speaking, you get more loss of lithium inventory. That makes sense. Higher temperature, more SEI layer growth. But also what you see is that the loss of active material in the cathode follows the trend of thermal gradients. And generally speaking, at lower temperatures, we get more loss of active material in the cathode. And actually, in most batteries, the cathode polarization dominates the resistance, right? And that's something that's not often captured in a lot of degradation models, and explains why at lower temperatures, because of the particle cracking, we get worse lifetime behavior. So really, we need to develop better models, and they don't currently exist right now to the level of fidelity that we want, of loss of active material in the cathode and the growth of the solid electrolyte interface for the cathode. So really, bringing it all together, understanding degradation is very coupled. So earlier, I showed you each degradation mode in isolation, but actually there's a path dependency involved there. So particle cracking leads to more surface area, more SEI layer growth, and that's really important to capture. So in terms of what we're doing, we're coupling these degradation modes. So if you do use PyBAM, open source, anyone can use it. We also have lithium plating in the models, so you can investigate fast charging protocols. Some of that is reversible as well, so you get chemical intercalation. We have SEI layer growth, particle cracking, and also loss of active material. And you can explore these different what-if questions. Now, just to wrap up and stay more or less on time, obviously we're in machine intelligence, battery intelligence talk, so got to throw some AI into the talk. So earlier, I talked about how we can use degradation diagnostic studies, and the conventional way of doing this is that we use open circuit voltage curve models. So basically, we have an anode and a cathode open circuit voltage curve, and we adjust each one to match the voltage curve of our system. And that's very useful. We can extract our loss of active material in the anode and cathode. What we did is we also thought about, in the real world, how do you actually operate these systems? And in reality, people rarely discharge down to 0% state of charge. So those lab conditions aren't very useful. You're more likely to have partial charge or partial discharge data, which we can use. So one of the approaches that we use is convolutional neural networks, which is a technique that they use in image classification. So basically dog, cat, that's the technique that they use to identify images. And we did the same thing, that we generated thousands of different open circuit voltage profiles from synthetic data with different degradation modes. So we artificially introduce loss of active material in the anode, cathode, and loss of lithium inventory. We have this huge database, and we train our neural network to recognize the pattern for partial charge and discharge in the system. And we can extract our loss of active material numbers, which we can then use to understand how the battery degrades over time and control it. So to kind of wrap that up, how do we kind of bring it all together? You've all heard about this digital twin concept, and I've been thinking a long time, what is a digital twin? Is it just a overhyped phrase of rebranding modeling? Maybe it is, but my interpretation of a digital twin is that it allows you to make asset-specific decisions that are optimal. So what you need to do is fuse real-time data collection with a physically relevant model, and you need to be able to forecast the behavior under different scenarios. So with that in mind, you can do lots of different things like optimize the state of charge range, the fast charging regime, and so on. But really, what we need is a holistic approach, where one of the problems in these physics-based models that we use, or DFM models, P2D models, or whatever you want to call them, is that it takes a long time to parameterize. In reality, people have the data about the conductivity, the particle size, distribution, and we as a community need to take a holistic approach of sharing data across disciplines, but also respecting that ultimately people will have intellectual property across each region, and we need to respect that, but there are definitely ways of doing that. And ultimately correlating like end-of-life knee point rollover with initial impurity data. And I think that's a very powerful concept. But anyway, last talk of the day, so let's kind of conclude it. So what we've seen is that degradation processes exist across multiple length scales. I've shown you some of the work that we do with phase field modeling of cracking, but also continuum level modeling of fracture coupled with SEI layer growth. I think chemomechanics is a really interesting area that people could be doing more work on. Obviously, I looked at idealized spherical geometries and also some non-ideal geometries, but we still haven't got a good description of how things like grain boundaries influences cracking and fracture behavior. We also need to look at how heterogeneous the current distribution is through an electrode, and ultimately what happens when you start to blend silicon into these anodes, and you can see it becomes even more nonlinear. And then finally, at the battery pack level, what you assume as 2C operation might not actually be that scenario. And you can get these kind of positively coupled systems or negatively coupled systems, as you saw earlier, which can lead to very different degradation pathways. So really, digital twins might be a vehicle for that. So that's basically what it is. Whilst I've got everyone's attention, just to kind of plug some of the things we're working on, Wei Han and myself are part of a special issue from Communications Engineering, which is Nature's new engineering-focused journal. So if you've got interesting work, please do make a submission. And we have open positions in our group to work on battery digital twins and also PhDs as well. So thank you very much for listening, and more than happy to answer any questions.
Thank you so much, Billy. Any questions?
Thank you so much for the great presentation. And if I know right, you generate the data for the electrode parameters to train the conventional model you show in that slide. And that came to the similar question that in this morning, that your machine learning model can learn the information that your physical model can provide. That means how the divergence of your machine learning can learn from the mechanical model. I mean that the mechanical model can simulate some specific degradation patterns with specific parameters, but you need to you need to generalize the model in different aging scenarios. So that could be the limitation for the generalization of the machine learning model. So that's my concern about how or if you any good opportunity or idea to improve the performance on those different scenarios. Thank you.
Great question. So I think in the next few years, no doubt, we're going to see more and more applications of AI and machine learning to battery applications. And whilst people say you can do a purely data-driven approach and a black box approach, I think we've got to be very careful with doing that, because you can end up misinterpreting the data or overfitting it as well. I think the field of explainable AI, where you kind of understand how the neural network works. So one of the pieces of work that we will be publishing soon is the application of explainable AI techniques to these neural networks. And what we find is that you can use various techniques. So there's one called CamGrad, which identifies which region of the image is the neural network looking at. So if you apply this to image recognition, you have a picture of a dog. If you apply these explainable AI techniques, what you find is that it focuses on the ears or the eyes and so on. And when we apply it to the battery voltage curve, it allows us to understand how the AI actually fits the model. And you find that it identifies certain regions that we as humans wouldn't initially intuitively look at. So I think we want to introduce that level of rigor across the community. There were some talks earlier about blending physics of what we know with data-driven approaches. And I think that's really important. But the final point is to think about these digital twins and these AI techniques, not in terms of deterministic approaches, but in terms of probabilistic vehicles, where essentially how does uncertainty propagate to the system and how do we interpret that? So hopefully that answers your question.
Thanks for your informative presentation. My question is, I see there are many beautiful results of the anode crack mechanical, and I also did some electrochemical mechanical coupled mechanism models. And I see there are also another publication see that anode mechanical stress is not affected too much in the EVs application, but the cathode is the most essential factor. So I wonder what you do think about this opinion.
Yeah, great question. So obviously in the examples I've showed, we focused on the chemomechanics of the cathode. So when you look at the mechanical properties of the material, so let me just kind of scroll back a bit more. Actually, I don't have the slides about the mechanical properties, but we focused on the cathode mostly because when you look at the properties, the Young's modulus and the fracture toughness of the materials are very ceramic-like, so they will fracture very easily. And they tend to be quite isotropic. The problem with graphite is that it tends to be quite ductile as a material, and also it's quite anisotropic because of the layered structure that you have there. So we have applied our fracture models to the cathode, and we get generally good agreement from a qualitative point of view. And also, if you can see from our phase fill model work, qualitatively speaking, it does match up. But I do think on the cathode side, there still needs to be work there in terms of understanding how graphite actually fractures. I think silicon is probably a good proxy, because silicon there is quite a brittle material when you look at the Young's modulus properties. But the challenge is your model is only as good as your input parameters. And actually, there's not a lot of people that provide that fracture toughness measurements of these materials. So it's a call to the community to not only focus on electrical properties, but also mechanically characterize the system.
Okay, thanks for your answer. And I have another question is, I see the multi-scale model, if I understand right, it is suitable for the guidance of the next generation battery, or the suitable charging or discharging profile, or the design of the batteries. So do you think it can also be used in today's BMS algorithm, or to guide our estimation, a lifetime, etc.? Thank you.
Great question. So with any multi-scale model, the problem is always like, how do you kind of, where's the image I had, pass information across length scales? Because the problem with those phase field models that I showed is that they're very computationally expensive. So if we, here, you're never going to fully model every single particle and then cascade that to a battery pack system. So the key is thinking about what is the key information. So the way we've looked at it for chemomechanics is that what we can do in our phase field models is extract parameters like the fracture toughness of the material, which is an aggregated material property. So Paris law generally fits to that. And then we can put that into a continuum level model. Then you're unlikely to solve a full P to D model or Newman model in an entire battery pack. So you might do some model order reduction techniques, so single particle models and more advanced techniques. I think it's also important to think about what you care about at the end. So it might be lifetime. And then in your models, to think about what are the stiff parameters. So you could argue a Newman model is ill-posed because there's 50 parameters and you're never going to be able to parameterize them all. But there are certain parameters in that model which highly defines the future lifetime of the system. And there are more floppy parameters beyond that. So you need to understand how uncertainty propagates through your system, and then design your model order reduction around what you want to get at the end, and the areas that you neglect and the areas that you focus more on. So hopefully that gives you some indication of our thinking.
Hey, thanks for the great talk towards the end of the day on the last conference. I'm Adam from Wärtsilä. We're a grid energy storage integrator. So we have really big power plants of a lot of cells. And we actually track the voltage of every cell. And so I'm really interested in your CNN work. Not just because it's fancy, but because we have a lot of field data, and this is that we have an interest in data-driven models because of that. The problem is we don't tell our customers how to operate the site in a lot of cases, and so here it looks like you were doing the partial depth of discharge under constant current. Please correct me if I'm wrong. So my two questions are: how critical to your CNN was the constant current to identify these features from it, because again, the current could be varying all over the place. And then the other question is, how important was the time resolution of the data? If you could try and comment on that as best as you can. Thanks.
Yeah, great question. So there's a few things to unpack there. I always kind of like to challenge the current thinking in the industry. And obviously we've got big data, and people think I'm going to collect loads of data, throw into an AI model, and it's going to solve all my problems. Now, we've run a few BMS projects where we've taken that approach. And actually, if you take loads of time series data, so take data every 1 second for 10,000 cells, you quickly end up with a data lake, and a lake can quickly flood you. And there's a cost associated with storing that on the cloud. So I think what you want to think about is, what is the information you actually want to collect? So our approach has subsequently been, okay, collect the voltage data, but then fit it to a physically relevant model. So we actually care about the loss of active material in the anode, cathode, and loss of lithium inventory. And actually with those three numbers, we can reconstruct what the whole time series voltage curve would be if you have the OCV model of that. So that's the first thing to kind of focus on. Now, we've obviously trained it up on constant current scenarios, and we've only really looked at that. I think depending on your scenario of how you operate the system, you can identify different features that you can then, ultimately it's going to be dependent on how you operate it, that will be useful. So you can also do it with resistance, where resistance could be to 1 second resistance or 5 second resistance, and you can start to infer it. Obviously, the more ideal scenario is constant current, but I'm confident that you can do it with more chaotic real-world systems as well.
We're going to do this question here, and then we're going to do, what I'm going to suggest we do is we have 3 great speakers with lots of insights here, and we're going to bring them up, and then we're going to have the audience sort of grill them. So we've got Jake, we've got Billy, and we've got Wen, who's still here. I don't think Nicholas is here anymore. So we'll do this one last question, and then it's a free-for-all for what you want, anything you wanted to know.
Hi, thanks for the talk. I was just curious about the error rate for the neural network, especially for the negative mass, because I suppose it's more complex. Yeah, that's my question.
Yeah, great question. So the challenge with some of these diagnostic techniques, if we're being completely honest, is that as your battery ages, they actually become less and less accurate. So that lack of accuracy comes from heterogeneous degradation. So if you think about a cylindrical cell, maybe in the center of the cell where it's hotter, you're going to get more degradation. And how these models work is that you assume they're all lumped. So obviously that starts to break down and the error increases. Our thinking as we move forward, so obviously this was work that is more deterministic in one sense, that you've got a single number, is to start to think about these systems as probabilistic in nature. So you have a spread in the results and you have a confidence interval there. So that's kind of where we're thinking. I think there's still value in terms of, even if you only have a health estimate that is 80% there, I think you can still do a lot of that. So what we've been doing is, if you think about degradation, if you're charging and discharging your battery at 2C, and you get a certain level of degradation, now a machine learning model might just fit linearly to that, and that's fine, but it might not capture that nonlinear roll-off in the battery. And physically, what's happening might be is that you are cathode limited in one instance if you've got more anode in the system. And as you consume that excess anode, you transition to a different mode. So I think identifying the physical transitions, which this technique allows us to do, allows you to understand and change the way you operate the system. So what we've been doing is augmenting the charging current based on the loss of active material in the 2 electrodes, because if you've lost 20% of your graphite and you're still charging at the same current, you're effectively increasing the C rate on the remaining active material. So hopefully that acknowledges that there is uncertainty in the system, which I think was your original question, but also ways forward in terms of maybe using like Bayesian statistical methods to understand how we can take, new measurements and increase the accuracy of future predictions.